And it's also two types, linear and non-linear. So that means this learning algorithm we can apply in linear models and also apply as a non-linear model. So if we want to define support vector machine, then we have to say that support vector machine is a supervised learning approach which used support vectors for classification and regression. So that means support vector we can use for classification and also for regression mechanism. Usually for classification, when we use support vector for the classification, we call it support vector machine or support vector classifier. And another one is support vector regressor. So what are support vectors? Then the support vectors are the data points, okay? The data points that are closer to the hyperplane. So few terminologies are there. So closer to the hyperplane and influence the position and orientation of the hyperplane. So position and orientation of the hyperplane, okay? So we need to understand also the hyperplane, okay, to understand the support vectors. We have the data set. In our data set, all those we call it data points, okay? And some of the data points we have to consider as the support vectors, okay? And those support vectors or those data points, it will be closer to the hyperplane. We will also discuss about the hyperplane. Hyperplane is just there is just the separating planes, okay? So that's called the hyperplane. And the support vector also actually influence the position and orientation of the hyperplane. Okay? So we will discuss those things in detail. Using these support vectors, the margin is maximized. Then another terminology here is the margin. So we need to understand also what is margin. Okay, margin is maximized by the classes. So here classifier is our support vector machine. So now we need to understand few things. What is support vector, what is hyperplane, and what is margin, to understand even the definition of support vector machine. So now consider that we have just one-dimensional data. One-dimensional data, that means we have just maybe few values. That is called one-dimensional data. So if we have one-dimensional data, like we can say that the mass, or we can say weight of few persons, and then based on the weight, we want to classify them like two classes. One class we can say that is the obese, and another one we can say not obese. Okay, obese and not obese. So based on the weight, consider that this is the weight, like maybe you can say the 50 kilogram or something. So here I is showing this nature. Okay. Now consider that this is the 50, and maybe you can say this is like 60 kilogram in kilogram, maybe in kg, okay, kilogram. And this is like maybe 65 kilogram of weight. Similarly, we can consider this is like the 75. Then this one is like 90 kilogram. Okay, so we have the data set. In the data set, just one dimensional data. It is given the weight, and based on the weight, we want to classify that whether this person is obese or not obese. So for that, we can maybe we can select a threshold like here. There is these are the according to the data set. These are the not obese, so no obese, no obesity, and these are the obese people. Okay, so obese people. That means they have the obesity. Yes, they have the obesity. And now we can see that actually what we have to do, we have to just set a threshold for that. The learning model, it will set a threshold, and that threshold, below that threshold, maybe no obesity, and upper that threshold, maybe you can consider that they have the obesity. Okay, so this threshold, maybe you can say we can just say that 66 kilogram or something. Okay, so this is the threshold. If we define the threshold equals 66. So here define the threshold equal 66. Maybe learning model will learn that. Okay, the 66. So our training data is here, and then we train the model, and then the model will learn that what will be the threshold for defining the obese and no obese. Okay. So if we just select here, that is if the model select here 66, then maybe the test case. Now, if we consider about the test case, one of the data point, maybe we can say here is the data point. This is the data point, and consider that this is just only 67 kilogram. So this is 67 kilogram of weight, and according to our learn model, that means according to our model, it will define the 67 will define as this will define as actually obese. Okay, yes, it has the obesity. Why? Because the weight of this one, of this new or test case, it is that is greater than the threshold value. So if weight is greater than the threshold value, then it will say that it is obese. Okay, maybe the model we have trained the model, that model will show this answer. Okay, it will show this answer. But the problem is, can we actually define this one, or can we say that this one is truly there is obese people? If we want to interpret that, then uh, then we can see that actually this is our test case, but this the weight of this test object, we can see very close to our no obese people. Okay, very close to our no obese people. This is no obese, the 65 kilogram, and here is the 67 kilogram. That means the weight difference is, we can say, just 2 kilograms here. Weight difference is 2 kilograms. But we can see that if we want to that is find out the distance from the obese people, like maybe this one, from this one, the weight difference in this case, you can say 5, 6, 7,
8.
2, 8. Okay, so that means total 8 difference here. So how can we interpret this? There is though the weight difference is just only 2 kilogram, but from the no obese, and higher weight difference from our that is, we can say, obese people, then why we are saying that this is the no obese people? This is no obese people. Yeah? Sorry, this is obese people. Why we are saying that? So that means in case of interpretation, or we can say, if we want to just explain the answer, no one will actually agree with us because the weight difference is too. Why you are saying that this is just obvious? Okay, so that's the problem in if we define the threshold like this way, that is 66 or something. Now, then what's the better way to define the threshold? Um, so for that, if we can add the two things like uh, the weight of the last people, we can say here last people uh, of no obesity. Okay, last people with no obesity, the weight of the last people with no obesity is 65, and weight of the fast people, weight of the fast people with obesity, we can say this one, it is 75. So if we divide this one by 2, that means if we find out the average, then we can see that the average, it is just 70. It is just 70. So now, if we set the threshold to 70, that is, we can say here, this is the threshold. This is the threshold equals 70. If we set the threshold here equals 70, then we can interpret easily. Okay, we can see that on that case, if the learning model will learn that this 70 will be the threshold, on that case, we can easily say that this one actually has no obesity. Okay, it has no obesity. That is the test case. It has no obesity. Okay, and it is also true because we can see this is closer from no obese people. That's why it is no obesity, and this has higher difference from the obese people. Okay, so that means if we can if we want to find out something, some threshold value at the middle point, then that will be better threshold for the separation. So we need to keep this one in mind. Okay, that means always we try to put the threshold here at the middle. Always we try to put the separation line at the middle. Always we try to put the separation plane at the middle point. So that's the logic why we are trying to put the planes or hyperplanes or the threshold or line at the middle. Okay, in support vector machine, we will also try to find out the hyperplanes, and that hyperplane we should put at the middle. Okay, here is this case. Okay. Now, so think about two-dimensional data, or you can say multi-dimensional data. So we already discussed about the one-dimensional data, just only weight we have, and we want to find out the threshold for that. But now we can set to two-dimensional or multi-dimensional data here. So in this case, we can see that maybe we will get few positives and few negatives. Same thing like there is obese and no obese. Uh, so for a data set, usually we consider something the training examples, okay? Training examples and testing examples. Sometimes we divide or partition our data set like 70-30, or maybe you can say 80-20, like this way. That means 80% for training purpose, 20% for testing purpose. Okay. So training examples, let's say we have a training set. This is our training data set. And in this case, we can see in this data set, we have 4 features. Okay. There is chest pain, and then whether there is any good blood circulation or not, and then whether any blocked arteries or not, and also the weight, weight of the patient. Then this is the heart disease. Okay, that means this is our class levels, or we can say target variables. So class level to classify whether a patient has heart disease or not. So for few patients, like this is the patient number 1, no chest pain, no good blood circulation, and no blocked arteries, and weight is just 125, and that patient has no heart disease. Okay? So another patient, patient number 2, and then he or she has the chest pain and also uh, good blood circulation, but uh, he or she had just blocked arteries, and also weight is 180, and then uh, uh, yes, that patient has the heart disease. Okay, so this is a data set. Maybe we can collect from any hospital or something. Okay, so we can see that uh, these are our class levels, so positives and negatives. So we can see these are our positives and these are our negatives. And based on the features, we can maybe plot those data points. So here in 2-dimensional plot or 3-dimensional plot, actually we can plot using just only 2 and 3-dimensional, but when we have multi-dimensional, we cannot see that picture. So consider that maybe we plot here using 3-dimension or maybe 2-dimension. Okay. So if we consider 2-dimension, then for separation, what we need actually for separating the positives from the negative, what we need. So for 1-dimension, we can see that just only threshold is enough. Okay, threshold, just only a threshold is enough. Just a point is enough to separate positives from negative. If we have 2-dimensional data, if we have 2-dimensional data, like maybe you can say x and y axis, we have x and y axis we have. Then on that case, a point is not enough to separate the positives from negative. Like if we draw a threshold like here, and that's not enough for our case. Okay. So on that case, what we need just type of line. Okay. We need this kind of line. So for separation of 2-dimensional data, we need at least a line to separate positive from the negatives. If we have the 3-dimensional data, then what we need? The 3-dimensional data, that means we have x, y, and z axis. Okay. We have another axis here, another axis, x, y, and z axis. So on that case, to separate positives from negatives, what we need? We need a plane. Okay. So not just only you can say that line, we need a plane like this to separate maybe positives from the negatives. But what we need when we have more than 3 dimensions, if we have more than 3 dimensions, then we need actually hyperplane. Okay, we call it hyperplane. Whatever the dimensions are, like 4-dimension, 5-dimension, 100-dimension, thousands dimensions. Okay, on that case, we need the hyperplane to separate positives from the negatives. So this is the concept of hyperplane, but how to define the hyperplanes? How we can define hyperplane? Uh, so, so like if we have 2 dimension, then we need the line. The equation for the line is what? Equation for the line is y equal mx plus c. So this is a line equation. Okay, that's the line equation. So in this case, we can see that the x-axis, like this axis here, x-axis, and here is the y-axis. So y-axis, that means based on the x, maybe we want to predict the y. Based on the x, we want to predict the y. But if we have more axes, like not only the x, if we want to predict y based on x and g. So on that case, here is the m, we can say m1 times x plus m2 times g. So that means based on the x and g, we want to predict y. So then we need this equation. Okay, we need this equation, and this is what? This is the equation of a plane. Okay, this is the equation of a plane because we have x, y, and g, 3 axes. So equation of a plane. Now, if we have more dimensions, like if we have like x, g, and also p, on that case, what will be the equation for that case? m1x plus of m2g plus of m3p. That means based on these three dimensions, x, g, and p, we want to predict y. So now we have total dimension 4. Okay, total we have 4 dimensions. So similarly, we have 5 dimension, 6 dimension, whatever the dimension is. Actually, our equation is this. Okay, this will be our equation. So this is our kind of one type of hyperplane equation: y equal m1x plus m2g plus m3p. So now the same thing we can also write a different way. Like we can say our prediction is the q. This is our prediction, and we want to predict this one based on our um, x, y. So like the m1, the equation we can say m1, then x plus m2 y plus m3 g plus of c. Okay, so that means based on x dimension, y dimension, and g dimension, 3 features, we want to predict q. Okay, so this equation we can write also a little bit different way. So here we can write this m1, instead of m1 we can write the w1 first dimension. Okay, and then plus of w2 of second dimension, that is x2, plus of w3 times the third dimension, like x3, plus c. Okay, plus c. So now this equation we can write differently. Okay, that means w1x1, w2x2, and w3x3 plus of c. If we want to find out that kind of equation, then now our equation is we can see here it is w1x1, w2x2 plus w3x3 plus c. The same equation. Now we want to represent those in vector form. So consider that we have the w vector, and in this vector we have w1, w2, w3. And this is our weight vector, or you can say that is the slope vector. Okay, slope vector. And we have another one that is our x. So this is our feature vector. And this feature vector consists of 3 features like x1, x2, and x3. So now if we want to find out something, like if we want to find out W transpose, so W transpose, that means this is in column, W transpose, it will transform to a row. And then W transpose X, we want to find out this. The product of W transpose dot X. Then it will be W transpose means it will be in row. And X is our X. Okay, so it is like a column. So now if we multiply these two, so you can see this one and that one. So here is the W1 times X1. So that means we will get W1 times X1 plus of W2 times X2. So here is the W2 times X2 plus of W3 times X3. W3 times X3. Okay, so that means W transpose X on that case, if we consider W that is weight vector and X is our feature vector, then W transpose X will give us this form. Now, if we add something, W transpose X plus of C or B, something, okay, then we will get what? We will get WX1, W2X2 plus W3X3 plus of B or C. This is what? This is our the hyperplane equation. Okay. So that's why usually we write the hyperplane equation as, this is the hyperplane equation. It is just only W transpose X plus of B. So this is the equation of our hyperplane. So that means the support vector machine, it will try to find out this kind of plane, okay, this kind of plane, that is W transpose X plus B. But what are the learning parameters here? That means what we need to find out, what are the values we need to find out, or what are the values we need to optimize. So usually in line equation, we have like, if we consider a line equation, here is y equal mx plus c. Just to draw a line, So we need to learn the m, we need to learn the c. That means the slope we need to find out. We need to find out the optimal value of slope, and we need to find out the optimal value of y-intercept. Okay. So for a single line equation. And here in this case, we can see that actually we need to find out the values of W and also the B. Also the B. So W, we can see W, it is now a vector. This is the vector. So that means we need to find out the values of W1, W2, and W3. So here, these are the learning parameters. W, that is W1, W2, W3, three learning parameters here, and B. Okay. So these are the learning parameters. That means in our support vector machine, we will try to find out the optimal value of W1, W2, W3, and also W. So now we need to understand the data set first. The training examples, we can see here X1 up to X1, and here is Y1 and Xn and Yn like this. Okay. So in this case, we can see for each example I, that means for each example here is the passion. For passion I, passion 1, this is the P1, passion 1. in this case, X is our feature vector. Okay, so X is our feature vector. So we can see these are our features. 4 features we have in this case: chest pain, good blood circulation, blocked arteries, weight. So these are our X. And Y is what? Y is heart disease. Okay, so this is our Y. That means we want to predict Y. So here in this case, X1, Y1, it means that these are the values. These are the values in case of our X1. X1. And this is our Y1. Similarly, this is our X2. So these are the values. That is the X2. So feature values of patient 2. And class level of patient 2, it is Y2. It is Y2. Okay. So Xi, that means X1. If we want to find out the first value, there is a first, we can say Xi of first feature. Xi of first feature. It means our first feature is what? This is our first feature. Feature number 1. Feature number 2 is good blood circulation. Feature number 3 is block arteries. And feature number 4 is our, that is the weight. So that means this is 1, 2, 3, and 4. We have 4 features. Here we can see this is 1. It means the first feature. And this is the last feature here is D. Okay, D is the last feature. In our case, D equal 4. D equal 4. And Y, in this case, we can see that Y is element of -1 and +1. It means the -1 means no, +1 means yes. Okay. So these are the positives and negatives we have. And the inner product we have already seen that it is the summation of W and Xi. So here this is the W and Xi, and this can be represented by the that is the hyperplane. So this is the equation of the hyperplane. Equation of hyperplane. W transpose X plus B equals 0. So this is the equation of our hyperplane, and we want to find out the hyperplane equation. Okay, hyperplane equation. So even though if we consider that our data set is just only 2-dimension, that means we want to predict maybe based on the chest pain, we want to predict heart disease. So if that is the case, that is one based on just only one independent variable, chest pain, we want to find out the dependent variable, that is the heart disease. And on that case, we have to draw the line. Draw the line. Okay? So we can put a line like this way. We can put a line like that way. We can put a line here. We can put a line there. Okay. So that means several lines we can draw differently. We can draw lines differently. But which one is the optimal one? Which one is the optimal one? We have to find out that. And we have discussed the linear regression and gradient descent. And on that case, we have also seen that actually, if we want to find out this kind of line, then we have to find out the optimal value of M and optimal value of C. Okay, M and C, optimal value of M and C. But here the method is different. Here the method is SVM, the support vector machine. The support vector machine also can find out the optimal line also if we just apply to a 2-dimensional data set. Okay, there is one dimension is feature, another dimension is our categorical variable values. Okay, so from this slide we can we have learned that how to formulate the hyperplane and what is hyperplane, and also there is we need to find out there is the optimal values of hyperplane so that we can draw different types of hyperplane, and that will be produce our optimal result. That will produce our optimal result. So now, as I already mentioned that is we need to draw the hyperplane. And if we consider that if we have just only 2-dimensional or maybe multi-dimensional data, then what we have to do, we have to draw the hyperplane. So consider that this is our kind of hyperplane equation. Here is the line equation. Okay. So now where to place that? Where to place that line? Where to place that line? So one thing is this, that is, if we place a line like this way, then for the test data, okay, maybe we can say we train the model, and maybe you can say, and then we have drawn this line. And now we can see that the test case, here is the A, here is the B, and here is the C. Okay, A, B, and C. And we can see that there is, for the C, the hyperplane, that is our line, is very close. And for the A, it is, we can say, very far from our line. And all these A, B, C, all these three, that is our test objects, are in one side, that is in positive side, okay, positive side. And we can say A is positive, B is positive, and also C is positive. C is positive. But if we think about our confidence, that is to say this one, that is A is positive, we are more confident. Why? Because this line actually very far from A. So that means we can say very far from A. Even though if this line is changed a little, maybe we can say during the training time, if it is changed here like this way, still we can say A is positive. Okay. And B is also, we can say B is also, B you can see it is also far from the far from our actual hyperplane. Okay, hyperplane. We are also confident about saying the class levels of B. But how about the C? We are less confident here, because it is very close to our line. Maybe if the line is shifted a little, there is, maybe you can say like this way, then the C, on that case, C, we have to say C is negative. So that means the distance from the separating hyperplane corresponds to the confidence of the prediction. So if some points are more distant, that is, position is more distant, that means placed in very far from the hyperplane, then we are more confident about saying their class levels. Because on that case, no confusion for that. Okay, a little bit, just maybe tilting, or maybe you can say shifting up or down. So that's why in this case, we are more sure about class level of A and B than the C. Okay, A and B, we are more confident, more sure about the class levels of A and B than the C. Okay. So from here, one thing we need to also actually think about that is, we have to place the hyperplane in such a way so that the data point, the distance of the data points, that those will be very high. Okay, that means the data point distance from the data point, it must be high. So that means we can say, we can maybe draw the line like this way, or we can say we can draw the line that way, or we can draw the line this way. That will not our actually goal. Our goal is to place the hyperplane in such a way so that the distance, or you can say the average distance of different data points, that will be high. Okay, so this is another our criteria to place the hyperplane. So one criteria we have already established our second slide, that is we have to place at the middle. And second thing we have to consider about, that is we have to place in such a way so that we can maintain the higher distance. So second criteria we already got. Okay. So here is the distance. We can see the distance, but that means we need to find out the distance. We need to calculate the distance anyhow. But how to calculate the distance? How to calculate the distance from point A to a hyperplane? How to calculate that? Okay, so I think we know how to calculate that. If we have just a line equation, like we have a line equation that is maybe you can say 3x plus 5y minus of maybe 6 equals 0. So this is a line equation. Okay, this is a line equation, and then consider that this is the line equation. Okay, and we have a point like here. This is the point. This point is about that is the Q, and this point is on 1 and maybe 1. So this is the point. Then what's the distance from this point to this line? So that means what will be the distance? This distance from this point to our line. And it must be the perpendicular distance, okay? The perpendicular distance. So for that, usually what we do, the distance we have calculated like this way. That is, we have to just replace the x and y by this point. Okay, so this equation. Okay, so that means it will be 3 times x. X is what here? X is here. X0 is x. So 1 minus of 5 times y. Y is what? Y is this one. That is 1. Y is 1. And sorry, not minus. It is plus. And minus 6. Okay, minus 6. Absolute value of that divided by square root of, there is the coefficient of x and coefficient of y. So x and y. So square of the coefficient of x, it is 3 square plus square of the coefficient of y, this is 5 square. Okay, this will provide us the distance. So in this case, 3, 5, that is 8. 8 minus 6 is 2. 2 by, here you can see square root of 9 and 25. So 9 and 25 is 34. 9 and 25. Okay, so 34. So this will be the distance. Usually we calculate the distance like this way. I think you already know this one because these are just high school math. We have already learned those things. Okay, so that means a line is given and a point is given. Then the distance from that point, the perpendicular distance from that point to the line, we can easily calculate. Similarly, if we have a hyperplane, that is the equation of hyperplane we know, and then we have a given point, then the distance from the hyperplane to the given point, we can also easily calculate that using this equation. So this equation is what? This is the hyperplane equation. We know that W transpose X plus B divided by, this is our square root of, there is coefficient. Okay, so coefficient here is 3 square and 5 square. So in our case, the coefficient is, you can say W2. W2 is what? W2 is our Euclidean norm. So you can see that it is just W1 square plus W2 square, W3 square up to Wn square. So this is our W2. Okay, so that means we can find out the distance. We can find out the distance from any point to the hyperplane. So now we have to think about our, there is the support vectors. So the data set is given. We can see that this is our data set. If we consider this data set, we can say here this data set, we can draw the hyperplane like this. So the dotted one, the middle one, the dotted one, you can draw the hyperplane like this one. Or even we can draw the hyperplane like that way. But now if we think about, if we draw the hyperplane using this way, we can say the distance from the hyperplane to the data point, it will be like this. Okay. Here, distance from hyperplane to, and if we draw this way, that is in this fashion, the distance will be, we can say this one and that one. The hyperplane we have to place at the middle. So that's why it is in middle. Here is also in middle, but this one ensures more distance. Okay, so this one ensures more distance than this one. That means the expected hyperplane is this one. This one is the expected hyperplane. So now we need to consider another thing, that is when we measure the distance, the data points closer to the hyperplane, usually we call those are the support vectors. So hyperplane, this is our hyperplane. So that data points closer to the hyperplane. So closer to the hyperplane, we can see here, this one is closer to the hyperplane. And this one closer to the hyperplane. This one is also closer to the hyperplane. So these are our support vectors. We can see here, if we consider class, this is the class A, these are the class A, and these are the class B. And if we consider this is our hyperplane, then this point and this one, or we can even consider this one, these are our support vectors. So in another way, we can also consider that is, at first we have to measure the distance from each and every point to the hyperplane. If we just consider drawing hyperplane, different way, like maybe we can say if we consider a hyperplane this way, then if we consider this is our hyperplane, then from this hyperplane to we have to measure the distances from all other points, and then the which one is closer to the hyperplane. Like in this case, maybe this one is closer to the hyperplane from the positive side, and this one is closer to the hyperplane from the negative side. So these two we have to consider as our support vectors. Okay, support vectors. So that means that's why it is mentioned that the data points closer to the hyperplane usually we call support vectors. And these support vectors, we can see if we place like this way, then this will be the distance. Here, this will be the distance, maybe the minimum. Okay, but we need to maximize this distance. Maximize the distance. So now we need to understand the margin. The distance from the closest example from the decision line or hyperplane is our margin. So we can say that this is our margin. This is our margin of this hyperplane. And this is our margin of our, that is this hyperplane, the fast hyperplane. And we need to maximize this margin. We need to maximize this margin. Why? If we maximize this margin, then it will ensure us there is all the data points will be in more distant. And that's why the margin we need to maximize. Okay, so we have already understand that is the support vectors and hyperplane. And another thing, there is margin here. We need to maximize the margin to ensure that is the data points will be in more distant points. Okay, so that's why we need to maximize the margin. Now, uh, so distance we have already seen that there is that this is our distance function. This is our distance function, and it is equivalent to this. This is our distance function, W transpose X plus of B. Here, all you can see that the phi of X, actually why we use phi, I will explain this one later. At this moment, consider that it is X, okay? The phi, actually, we need to transform. Sometimes we need to transform the data points into a new space. That's why the phi is given, okay? It is a transformation function. So consider that at this case, no need of transformation, just whatever we have, we want to use that. So this is W transpose X plus B, and then here is the W2, okay? So this is our distance. So using this distance function, what we have to do? Okay, at first we need to find out the distance from the hyperplane. Okay, that means here to hyperplane, here to hyperplane, the distance. Okay, we need to measure the distance. We need to measure the distance. Measure the distance. Okay, and then we need to find out the support vectors with minimum distance. Okay, minimum distance. So we can see here the minimization of this distance function to get what? To get the support vectors. We need to find out the support vectors. Okay, and for that, we need to find out which one actually in minimum distances. Then in this case, we can see from the positive side and from the negative side, we will get this one maybe one support vector, this one another support vector, this one is another support vector. So we can consider these three as the support vectors. So here it is the minimization. And then another term here is that there is a maximization. Why the maximization is necessary? So we have to find out that is the hyperplane in such a way so that it can maximize these distances. That means it can maximize the margin. And that's why it is maximization based on the W. What is W? This W is actually our, that is the vector. W is our vector. And this vector is weight vector, or we can say slope vector. We need to change the slopes. We need to change the slopes to change the lines, okay? That is change the hyperplane, this hyperplane. And maybe we will try different, that is values of the W. And for each and every time, we will try to find out the distances, that is, and find out the support vectors. And then among all these variations, we will find out the W which will maximize this margin. We will find out the maximize this margin. Okay, so that's why the function here is to minimization, the maximization over the minimization. So that means the goal is to maximize the minimum distances. So this is our objective function in our support vector machine. Now, the thing, we already incorporate two things, that is support vectors we need to find out with minimum distances. And another thing is we need to maximize the margin. That's why we have already seen this equation. But the problem is we didn't consider still that is the correct or incorrect classification. That means the accuracy. We didn't consider, still we didn't consider in this equation, we didn't consider about the classification accuracy. That's why we need to incorporate something here. We need to add something here to actually to uh, for our accuracy, for increasing the accuracy of our classification. So that means if we apply this equation, then it can draw the line differently. Like it can draw line like this way, or it can draw line like that way. Okay, to maximize just the distance and also the support vectors. But that's not our goal. Our goal is to find out the correct classification. So we have to place the support vectors in such a way so that in one side, maybe we can say we need to get all the positives, in another side, we need to get all the negatives. So now we have to incorporate that constraints also in this equation. So now how to classify? So if we can say, if we have a line like this, so few points will be in above the line and few points will be below the line. So whether that is all these points above and all these points below, it will correctly classify or not. So for that, what we have to do, we have to test this one. That means W transpose X plus B, we know this equation. This is our line equation, or you can say our hyperplane equation. This is there, this line equation, hyperplane equation. And then if something that is above that, so this one is above that line. If we consider that these are the positives, okay, above the line is the positive, then all the data points above that, it will be positive. If we can see that if we put that value in this, that means like if we consider a point here P and X, Y, X and Y, this point, what we have to do, we have to put those values here, okay, in this equation. And if this equation, that if we can get the greater value, it means that it is above the line. Okay, so that is the positive group or positive class. Similarly, if we get the negative value, it means it is below the line. Below the line. That means it is that is below the line or below the hyperplane. Okay? So we can say we consider those one as the negative value. So that means in hyperplane equation, if we put the values of any data point, then if that we get something like the positive value, that is we can consider that the positive, and negative value we can consider the negative. But the problem is, so here it will give us the positive and negative. That means it will give us the predicted result. It is the predicted value greater than 0. That means we can say positive, and less than 0 is negative. So this is our prediction based on what? Based on our W. Based on our W will actually shift our lines here and there. So then it will give us the prediction. But we have to think about now our original. It will give us the prediction, but what's the original class level of that point? So now we can see that the original class level we will get from the data set, that is our Y. We have already discussed about that. That is Y. Here, we can see if we consider the data set and our Y, you can see this is Y, heart disease. So no, it is -1. Yes, it's +1. Okay. So that means in our data set, this will be given. This will be given because it is supervised learning. Okay. So this will be given. So that means original data point, original class levels, we know the original class levels. We know the original class levels, and we also know the predicted class levels because already we learned maybe W and phi of X, okay? Based on W and X. So now we can see that this is our hyperplane and this is Y. So from here, we will get the prediction, and this is the original. So now if we multiply these two, if originally the class level is positive and our prediction results are also positive, that is predicted value is also positive. So this one we will get from y I, and this one we will get from our hyperplane equation. And then we can see if we multiply these two, this is correct classification, okay? Originally positive and hyperplane is also mentioned positive. So if we multiply these two, then we will get what? We will get the positive result. Originally it is negative, and our hyperplane is also mentioned that it is negative. Negative. If we multiply these two, then we will get what? Positive value. Okay. These two actually correct classification. Okay. These two correct classification because original and predicted is the same. But now, if we consider original, it is positive, but our hyperplane equation will mention that it is negative. So if we multiply these two, then we will get what? We will get the negative result. That is, this is incorrect. Okay, this is incorrect. Incorrect. Similarly, originally it is negative, and our hyperplane equation will say that it is positive. That means this is also incorrect. And for that, we will get what? We will get the negative. So that means we can see that if this multiplication of these two is positive, then we will get the correct classification. Here, that is mentioned. If it is greater than or equal 0, that is positive. Then we can say this is correct classification. And if we get something negative that is less than 0, it means it is incorrect classification. So we want to incorporate this concept to our equation. So previously we had this equation. Okay, this is the equation. We need to find out the optimal W based on this. That is argument of W max and mean dh. That is the distance. Okay, so distance function, we know that this is our this is, and that one, this is our distance function. Okay, and now we can see that we have to multiply this part by yn. And then we can see that is this is instead of just dh, here is w transpose this one and divided by w2. Okay, so that means now the equation for finding out our optimal values of the w, we have to consider this. So that means the minimization of this part, it will give us the support vectors, and then there is the maximization over w. It will provide us the maximum margin, and then this yn time this one, it will give us our the correct classification. Okay, correct classification. And so this is the objective. Okay, this is the objective. Now we want to write this one in the form of optimization function. Okay, in optimization function, usually we have a objective function and few constraints. So we want to write this one according to that. Okay, so here we can see that the distance, whatever the distance from the from our support vector, if we, that is rescaling that to just 1, okay, then other values will be maybe different. So that is kind of the rescaling. So here we can see that after rescaling, we can see we need to find out this one is the 1. Okay, and in that case, it will, original equation will be w transpose x plus b equals 0, and this one, that is our negative garter. This one is our positive garter. Okay, positive garter and negative garter. So that means that originally, now we want to we want to rewrite this function using the optimization function. So in optimization function, we have the objective function and the constant. So we want to rewrite that. Uh, so previously, this one W transpose X, it is this W max 1 by something, then this is called such that, okay, such that this is constant, such that minimization of this equal 1, okay. So what does it mean? Uh, it means that we can see that that is positive 1, and this from this part we want to find out maybe either positive 1 or negative 1 something. So that's why here is 1, okay. So we can say 1 times 1 is 1, okay. But actually this part, from this part we will not get only the positive 1, we will get positive value or negative value, okay. We will not get always the positive 1 exactly 1, not. So we will get from this, we will get the positive value. So positive value or negative value. And that's why the constant we just little bit writing this one greater than equal 1. And here is this part, this is the maximization. Actually, this part is our margin. It will ensure our margin, the maximization of margin. So maximization of 1 by W2, this is the maximization function. But same thing we can write differently. But this is 1 by something. The maximization of 1 by something, like maximization of 1 by x. It is the same thing that the minimization of x. If we minimize x, then we will get the maximize of 1 by x. Okay. So that's why we can rewrite this equation here this way. That is, here's the maximization problem, but we now it is a minimization problem. Minimization problem. So minimization of W. And additional thing we can see here, half. This half is added, and this is for mathematical benefit. The mathematical benefit, this half will provide us the mathematical benefit. Specifically, if we try to solve this one using like the gradient functions, okay, then the gradient just the sum of squared residuals, if we consider that, then take the derivative of that, then again the 2 will come in front, and 1 by 2 times 2, just cancel those out. Okay, that's kind of benefit we want to get. That's why the half is added. That's half of W. So this W is what? This is our actually Euclidean distance. Okay, so that is Euclidean norm. Euclidean norm, and we previously we have seen that this W, uh, there is norm 2. That's why here is the 2 mentioned. This is called norm 2, and that is Euclidean norm. It is actually square root of W1 square plus W2 square. In this way, we have to write like Wn square. So this is the W2. And we know this equation also. Okay, we know this, that is Yn is our original class level, and Xn is our feature values. Okay, feature values. So we need to find out the W and also B. We need to using the optimization theoretic approach. So this is called the SVM with hard constant. SVM with hard constants. Hard constants means, so here we can see that this one must be greater than or equal 1. It means that we want to find out W in such a way so that all the data elements we want just correct form, or you can say we want 100% accuracy. So that's why it is called hard constant, because it will not allow any misclassification. So that's why it is called hard constant. Okay. So we need to find out W. We need to find out in such a way so that this equation holds. This equation holds. If this equation holds, means it will find out W in such a way so that it will not allow any misclassification. So always it will just allow the correct classification. Okay. So this is called SVM with hard constant. But we know that there is hard constant. This is sometimes it is not possible. Okay. So on that case, maybe it will not uh, provide us any solution. One problem is this, and another problem is there is in training time. If we want to classify 100%, or we can say we want this 100% accuracy, then sometimes your model will be overfitted, and that's why we need to have some flexibility of misclassification. That means we need to incorporate something so that it can allow few misclassification. If we allow few misclassification in testing time, or we can say when we apply the the the, the test set in our model, then on that case it will perform better. And we have already discussed those things in bias and variance problem. Okay. So that's why we need to allow few misclassification. Okay, but at this uh, those things I will discuss in our next class. But uh, at this stage, if we want to find out that the optimal solution, then how to find out the optimal solution? So this is an optimization problem, and we can use several optimization methods to find out the W and B. Okay? W and B. So one of the popular method is called Lagrangian optimization. Lagrangian optimization. So I will discuss the Lagrangian optimization. Uh, just we can start here. Okay? We can start the Lagrangian optimization. So in this case, we can see that we have to we can write here minimization 1/2 and W, and such that this is the case. So in optimization form, we can write like minimize 1/2. This is that case W, and then subject to constraints. This is the subject to constant. So such that this condition holds. So now, what we can write? At first, we can write the Lagrangian equation. We can form the Lagrangian equation based on these two. This is called the objective function, and this is called our constant. So these constants and objective function. At first, we need to make these constants as it is inequality. You can see that there is a greater than equal 1. So at first, we need to make it equal. That is equivalent, okay, equality form. So that means it will be yi wxi plus b minus of, if we just shift this one here in left hand side, then it will be minus equal. Okay. So the equality form. And then in Lagrangian equation, what we have to do, at first we need to put the objective function. So this is our objective function. This is our objective function. And then for each and every parameter values, we have to add, or we have to incorporate the Lagrangian constant. So we can see here wi, wxi something, but this w is actually we have some the w vector, okay, w vector. So here in this case we can say wi. That means we have to consider, we have to sum up for all I. So here is the summation. That's why. And this alpha I, this is called our Lagrangian constant. Okay, so Lagrangian constant for each and every data point. So Lagrangian constant. So Lagrangian constant yi wxi plus b minus of 1. So here the xi and yi. So we need to consider only the support vectors for that. Okay, support vectors, not the all data points. We need to consider the support vectors only. And alpha I is our Lagrangian constant. So this is how we have to form the Lagrangian equation. The Lagrangian equation is this. That means at first objective function. So usually what we do in Lagrangian form, Lagrangian equal at first the objective function, whatever the objective is, then minus of the Lagrangian constant like the alpha. Then we have to use our constant. So the first constants here, like constant number 1. If we have more constant, then we can say this is our alpha 1, then alpha 2, then constants 2, like this. Okay, so this is the basic form of Lagrangian equation to form the Lagrangian equation from any optimization problem. Okay, then we can see here the Lagrangian. This will be the case. Okay, this will be the case. And so this is our Lagrangian. But now what we have to do, the next thing is now we have to take the derivative of this equation, with respect to W and with respect to B, to find out different form of equation. And finally, we need to find out the values of Lagrangian constant and also the optimal values of W and P. So here, this is our equation, Lagrangian equation. So take the partial derivative of this equation with respect to B at first, with respect to B. So we can say it is delta L by delta B. So if
Sir,
we take the derivative,
sir, I
yeah.
have another class right now.
Oh, okay.
Same, sir.
It's already
Okay. So we
10.
can, I think we can stop here and we can start our next lecture from this slide.
Okay, sir. Thank you.
Okay. Okay. Thank you very much.
Assalamu alaikum, sir.
Alaikum salam.
Sir, I have a question, sir.
Yes, please.
স্যার আমরা স্যার আমাদের মিড মার্কস কবে জানতে পারবো?
As soon as possible আর কি। আমি খুব তাড়াতাড়ি দেওয়ার চেষ্টা করব। Within this week maybe.
ওকে, থ্যাংক ইউ স্যার।
Assalamu alaikum, sir.
Alaikum salam.